Okay, now I'm hitting go. All right, so here's the new stuff. So for today, we're just going to get started on this. But what we want to talk about today, there's another species of limit here that's really important to us. We've talked about regular limits, and then we talked about these weird infinite limits where we approach an asymptote from one side or the other, and we get an infinite answer. Okay, well, we can also do something like, I guess we'll title this limits at infinity. So we can take limits as x approaches positive or negative infinity also. And that's a really useful thing for us to do because we oftentimes want to break the behavior of a function when we think about the behavior of a function. Like say we've got some function we're graphing on the xy plane. This whole region in here where we usually focus all of our attention, we could call that maybe the local behavior. The local behavior of a function might do all kinds of crazy stuff, right? But we oftentimes also want to look at the end behavior. We want to look at what's happening on the tails of the function, way out yonder, there, or there, right? And so this behavior out in this region, out that way or out that way, is the end behavior. That's important too. And that's kind of what we're getting at when we talk about limits at infinity. Okay? Physically, if we're looking at a system, a lot of times we might want to say, well, what happens if we extrapolate forward in the system as t goes to infinity? What's going to happen? We physically do that kind of thing quite a bit. So let's start off by just defining what a horizontal asymptote is. So a horizontal asymptote just means that if the limit of f of x as x approaches negative infinity or the limit of f of x as x approaches positive infinity equals some constant value, then we call that a horizontal asymptote, right? Means that as you go further and further out to the right, for example, if we're going to, if we're going to stick to some asymptote, then that's a horizontal asymptote. I'll give you an example of one. If we just look at, for example, let's just make one up here. What if we just take the function, I'm just going to make one up, y equals, let's just say 6x divided by, oops. Oh, what am I doing? 6x. Divided by, say, 2x minus 3. Okay, there's the local behavior of that function is all kinds of crazy stuff. We get a vertical asymptote, it's doing all kinds of crazy stuff. But if I go out infinitely far away, notice that it starts to get very flat and horizontal, right? And that's a horizontal asymptote, okay? The further we go out, it doesn't change, right? Okay? So let's look at a couple of examples here of how we're going to, in order to do this, we need to utilize two relationships, and these will make sense. The limit of c over x to the r as x goes to positive or negative infinity is 0. Okay. That makes sense? How come that works? Just in a nutshell. Somebody raise your hand and describe that to us. Explain to us what's going on. C is some constant. What happens? Why does that fraction go to 0? You make that bigger? I can make this bigger. A little bigger at least. How's that? Oops. How's that? What's happening with that? Liz, can you think, why is that, why are those fractions going to 0? As x goes to infinity, what's happening to that that's making that thing go to 0? Think about just the behavior of a fraction. How do you make a big fraction? How do you make a fraction that has a big value? And how do you make a fraction? Okay, good, right? Would you agree that if you increase the numerator of a fraction, it gets bigger, but if you increase the denominator, it gets smaller, right? So if we just take that trend and extrapolate it out to infinity, well then, if the bottom's getting infinitely big, the top is just left alone. It gets dwarfed, and you get this incredibly small fraction. So they're both going to tend to 0, aren't they? Right? Makes sense. Okay, and then there's another one here that's going to seem a little weird for the moment, but we'll get back to this one later. So let's deal with it now. We won't talk more about it today. But while we're on this slide, we'll just take a quick look at it. Okay, what about this one? What does E stand for?
Isn't it Euler's number?
It's a natural constant. Sometimes call it the natural number. 2 point, what is it? I don't even know. 7128 or something. It goes on and on and on. It's just like pi. It's one of those numbers that just goes, it's a number that shows up a lot. This year you'll learn why E is the value that it is. You know, when we review exponential and logarithmic stuff, I'll prove to you why it is, why it has the value it does. But for now, we'll just take it, just some natural constant. So if we take an exponential function, base E exponential, right? So that's ringing a bell from last year. Okay. If we take a base E exponential, so e to the x, and x goes to negative infinity, does it make sense that that's equal to 0? Okay, well, what is, if I take the limit, I remember how I deal with this. Do I have, no, never mind. Okay. So if x is going to negative infinity, what is this becoming? Think about e to the x. If I'm plugging a negative exponent in there, what do we do? What's our exponent rule tell us when we plug in a negative exponent? What's that become? Well, but how, like if I have, just in general, like a to the negative m is what? Right? Okay. So if I'm plugging in a very large negative value, isn't that going to be the same thing as saying 1 over e to the absolute value, is making it positive? Does that make sense? Okay, so like if I e to the negative 1 million is the same as 1 over e to the 1 million. Well, e to the 1 million gets pretty darn big, isn't it? Right? So you can start to see the trend here. The bottom, once again, is going to explode while the top stays captured at 1. And you get this vanishingly small fraction. Same thing up here, right? If we've got e to the minus x, that's the same thing as 1 over e to the x. If I'm plugging in huge numbers, same behavior, right? Okay. And if we want to look at those just to jog your memory, what those things look like, here's so there's e to the x, right? And there's e to the minus x. In both cases, that makes sense. As x approaches positive infinity, the blue function approaches 0. Okay? As x approaches negative infinity, the red function approaches 0. Okay, we can see that. Also, how about this? So what if we take f of x equals c over x to the r, just to demonstrate what we talked about earlier? I can slide this around, so it doesn't really matter what c is. If c is a positive number, all that's doing is the bigger the number, the more it's stretching it vertically. If I make it negative, it just flips over. But in either case, the asymptotes, the horizontal asymptote is at 0, isn't it? Okay. Doesn't matter what the value of r is. If I make r bigger, if it's odd, then we get this weird two-sided vertical asymptote. If it's an even value, we get a one-sided. Changes the shape slightly, but who cares? It doesn't affect the overall end behavior, does it? It still goes to 0. Okay, so let's try some limits then. So what if we try to do one of these things? We take a limit at infinity. How about this top one? What do you think we can do with that? Ideas. So if I've got a limit of a sum of terms, I can just break it into separate limits, right? And we don't have to write this out necessarily, but this really just becomes the limit of 5 plus the limit of 3 over x squared. What's the limit of 5? 5. And then how about this guy? As x goes to infinity, 3 over x squared goes to 0. So we just get 5. How do I get 0? Because if I have the limit of a number divided by a power of x, remember that's what we just said, right?
Oh, okay.
That make sense?
Wait, no, it doesn't make sense.
Okay.
Okay, right there.
Okay, it's the one right there. Right? If the bottom of the fraction explodes, the fraction goes to 0. Right? So the bottom of that fraction is getting infinitely big. The top is just staying 3, and so the fraction goes to 0. Yes, sir?
Doesn't necessarily have to have a power on the bottom from 1 over x also if you.
Well, that's a power. What's the power of x there? 1. No, 1. Yeah. So how about this then?
Then.
3 over e to the x. Well, that's the same thing as saying, we could rewrite this, couldn't I? That's just 3 times e to the negative x. We don't even have to do it, but that's how it matches what we just talked about, right? The form we just talked about. What do we do with the 3? Bring it up front, good. So then we get 3 times the limit of e to the minus x as x approaches infinity, and that's one of our limits that we just talked about. What's that? Goes to 0.
Couldn't we change e to any number though?
Sure.
Okay.
We could, yeah. We're just using it to be any base. And so that goes to 0. 3 times 0 is 0. Okay? All right, so now this is, how much time we got? 5 minutes? Okay, so this is good. So we'll just, let's look at, I want to look at 3 examples, and maybe we'll just get through the first one today. Then we'll pick up tomorrow with where we left off. So how do we deal with one like this now? If I let x go to infinity, what happens if I try to evaluate this directly?
You get infinity times 3 plus 5 over infinity squared.
Okay, so what is 2 times infinity plus 5?
Infinity.
Everybody agree that's infinity? Okay. So if I try to evaluate directly, I get infinity over, so yeah, what's 3 times, and when I say this is not correct. Infinity is not a number. You can't just do operations on infinity. This is, you got to take this with a grain of salt, but this is kind of the way mathematicians would talk about this. It's a limit, but if you're taking a huge number, right, 3 times, call it infinity squared plus 1, what's the answer? Okay, but what's infinity squared? Infinity. Okay, infinity over infinity, can you guess what that is? No.
Infinity.
No, that's just like 0 over 0. That's one of our many indeterminate forms. We'll talk about more throughout the year. But the 2 what we generally use the most, run into the most, would be 0 divided by 0 or infinity divided by infinity. Those are both indeterminate forms. They could be anything. We don't know. We got to do more work, in other words, right? So we need some more work to resolve the indeterminacy, okay? So what's our work gonna look like? Well, let's do, more work means algebra. We've gotta do something inside the limit to make it look different so that it's no longer indeterminate, right? We are gonna come up with a very simple rule that's gonna allow us to avoid any work on these, but we're not there yet. So for now, we've gotta somehow resolve this. Any suggestions? Wait in. Okay, factor what? What?
Factor what out to nothing.
Now, what can I factor? Okay, factoring, I don't think it's the kind you're thinking of, but it's actually how we want to proceed with this. Okay. What if we factor something out, like the top and bottom?
No, we split it.
What? X? Okay,
We split it.
that's the right track. You could do it with an X. Let's do it with the biggest power of X that shows up in either the top or the bottom. You could prove this, that would work too. We could take an X out, and that would work also. This, I think, maybe is a little bit easier. If we factor out an X squared from the top and the bottom, you tell me what's left over. So let's do the bottom first, because that's pretty easy. If I factor out an X squared, I'm undistributing an X squared, so I'm dividing each term by that to see what's left behind, right? So what's left from this term if I factor out an X squared? 3. Okay, plus, what about this one? Yeah, everybody see that? Okay, and you can prove it to yourself. If I redistribute the X squared, yeah, I get back my 1, so it works, right? On the top, what are we left with? 2 over X. Agreed? And if you're wondering how you get that, well, one way you could do that, if you want to connect the dots, and I'm running out of time here, is we could just say 2x over x squared equals what? Oh, yeah, that's just 2 over x, right? Okay. And then finally, plus 5 over x squared. Everybody agree? Okay, algebraically, we can cancel those, right? So we're left with the limit of 2 over x plus 5 over x squared divided by 3 plus 1 over x squared as x goes to infinity. And what happens to 3 of those 4 terms? No. They go to 0, right? If I've got x's on the bottom, 0, 0, 0, and we're left with 0 over 3, which is what? 0. Boom, we got it. Okay? We'll review that tomorrow and finish it up.